Hi everyone, we'll be talking about enzymes today. It's just me and Pete. What are enzymes? Well, enzymes are mostly proteins that catalyze chemical reactions. I say they're mostly proteins because there is a class of enzymes that is RNA based. We call them ribozymes. But for today, we're only going to be concerned about the proteins that are enzymes that are proteins. Enzymes work by lowering what's called the activation energy of a reaction. And in the next couple of slides, we'll be defining what the activation energy is. But they do this by basically providing an easier physical conformation or physical interaction for the reactants to form products, or they can couple the unfavorable reaction to a favorable reaction, such as ATP to ADP. Now remember, ATP is considered the energy of cells. So using energy to make a more favorable reaction. What I have here on the y-axis is energy, on the x-axis is reaction progression. The red curve is a reaction without enzyme. So this addition of energy above the system, this hump here, is called the activation energy. So it's quite high. So the reactants and the reaction cannot get over this activation energy because it requires such a energy input, such a high energy input that the reactants are unlikely to form product. It'll happen, it'll just take a very long time. With enzyme, we notice the activation energy is much lower, so they're catalyzing the reaction. And we find that the reactants can go over this hump fairly easily and then form product. An easier way to visualize this is using a system Callum explains science with cats. What I have here on the left are cats or reactants. On the right here I have products or cats in boxes. Everybody wants the cats in boxes. The cats want to be there. I want the cats in boxes. But in between the cats and the boxes is an activation energy barrier in the form of a water fountain. So it would take a great deal of energy for these cats to jump over or to jump through this water fountain. So it's a large activation energy barrier. One cat managed it. He was a bit of an odd duck, but he managed it. So this can occur without enzymes, but it's unlikely to happen, or it will take a very long time. With enzymes, we reduce the activation barrier. So more cats are going to be able to jump over this water fountain or jump through it. And as such, the cats, the reactants, will form products or cats in boxes. Once again, we will get cats in boxes over time, but with the addition of enzyme, it's going to happen much more frequently and much faster because this activation barrier is much lower. So thank you, Pete, for giving me this amazing metaphor. Truly, he's a leader in science education. We'll kind of work through a couple more metaphors. Enzymes are understood through a couple of models. One is the lock and key model. It was published in 1898. It's still around today because it's relatively relevant. What I have here is the enzyme with two active sites. You notice the active sites match the substrates perfectly. So the substrate binds to the active sites to form the enzyme substrate complex. The catalysis occurs, and then the enzyme, this becomes an enzyme product complex, and then when the products leave, it just becomes enzymes and product. The lock and key metaphor, there's one key for one lock. When they dock, it's a perfect match. They always were meant for each other. And so it's just a lock key complex metaphor. The induced fit model came out 60 years ago, and it's a little bit fuzzier around the edges. So rather than have a dedicated lock and a dedicated key, the enzymes are a little bit more reactive or responsive to the substrates. So what I have here is an enzyme. You notice the active sites do not resemble the substrates. So really, when the enzyme starts to interact with the substrates or when the active sites form. So rather than perpetually and always having the active sites ready, it does require the interaction between the substrates and the enzyme to form the active sites. So it's the enzymes of the enzyme substrate complex, which is the same. We're not showing the enzyme product complex. It was just missing in this figure, but it is there. And then the enzyme and the product go off their own merry ways. One consequence of this model that has been shown to be true is that enzymes can have multiple different kinds of substrates, so they're not limited. So not all enzymes have multiple substrates, but a few do. So it's not just a one lock, one key situation, but some enzymes are one lock, but they can have multiple keys, multiple substrates. So whichever model helps you get to the point where you understand the docking and the enzyme substrate complex to the enzyme product complex, feel free to adopt that, but just understand, if you prefer the lock and key, that it does the interaction between the enzyme and the substrate frees up the active sites, and some enzymes can have multiple different kinds of substrates, so multiple different kinds of keys will work. But aside from that, it's a really nice metaphor. So I just wasted 5 minutes of your time. Why should we care about enzymes? Why should we continue with this online introduction? Basically, enzymes allow life as we know it. Without enzymes, we're all dead. That's a bit dark. So on a lighter side, we use enzymes in many different industrial applications. We use it to brew beer, we use it to bake, we use it to clean. We use it in pharmaceuticals. Basically, there are a plethora, a wide range of applications for enzymes, not just in keeping us alive, but enriching life and building a more sustainable kind of way to perform chemical reactions. And we can find enzymes anywhere, which includes our own spit, which is the segue to the second and last portion of this introduction. Our spit actually contains a class of enzymes called amylases. Amylases are responsible for degrading starch to glucose. And many of you will have done this demonstration in the past, where you take a cracker, chew on it, leave it in your mouth for 10 to 15 minutes, and suddenly the cracker tastes sweet. So this is because the starch is being broken down. You can see it's just a bunch of monomers of glucose stuck together by the amylases to form glucose. And glucose is sweeter than starch. So that's why when you chew on the cracker for 15 minutes, it becomes sweeter eventually. Hopefully. So sweetness is a bit hard to define and put a number to. I want to actually know, how much starch can my spit convert to glucose? There are a lot of industrial applications for this. In biofuels, we can degrade vegetable starch to glucose, so the yeast can then make ethanol from it. We can biorefining, we can convert starch to glucose, then sell the glucose because it's more expensive than starch. So basically, do I have a cash cow going on with my spit, or is it a bust? So I want to know, how much starch can my saliva degrade? The experimental design is based upon the fact that when starch and iodine come in contact, they form a lovely blue dye. So this solution has no starch. You can see that it's clear. There's a little bit here, so it's a little bit blue. An intermediate amount here, so it's moderate amount blue. And then here, these two are much more blue. So we can actually quantify the amount of blue in these solutions to quantify the amount of starch in them. So the experiment is relatively simple. We take a known amount of starch. We then add in a negative control, which is nothing. A positive control, which is an amylase I bought at the store. Or we add in spit at 3 different concentrations. Pure spit, spit that I've diluted 1 to 10, and spit that I've diluted 1 to 100. And then I incubate for 37 degrees Celsius for 30 minutes. And then I compare this to known quantities of starch that I treated with iodine. So, very simple experimental design. Unfortunately, I did this yesterday, and we're going to have to make some improvements in the future. But we'll talk a bit about them because it's important to understand where I went a little wrong. What I have here on the y-axis is absorbance at 620 nanometers. 620 nanometers is in the blue spectrum of visible light. So basically on the y-axis, consider this the amount of blue, the blueness. On the x-axis, I have percent starch remaining. So 100% was that no starch was degraded. 0% is all of the starch was degraded. And instead of finding a nice straight line, I have a hideous logarithmic curve. To get around this, I cut the curve here, and now I have a nice linear line wherein I can fit a trend line, which is this dotted line, which gives me an equation and something called an r-squared value. The r-squared value is reflective of how well the points match the line. So the closer to 1, the better the points match up with the line. Our r-squared value is 0.995. We can say with a fair degree of confidence that the points fit the line. The line fits the point. So we can fit our treatments into this curve to try to figure out how much starch is left. Here I have my standard curve treatments in case you wanted proof that I'm not making numbers up. 0% starch, 1% starch, 5% starch, and then 10% starch. You can see it becomes more and more blue. What I have down here with this very blue sample, so quite a bit of starch left, is my spit diluted 1 to 100. Next to it, with this very clear sample, so not much starch left, I have my 1 to 10 dilution of my spit. Here I have my pure spits, also very clear, so not much starch left. And then I have my positive control, the amylase I bought from the store. It's an intermediate amount of blue, so we had some starch degradation, but not totally. These arrows point to where these treatments fell on the standard curve. My positive control was perfect. It fell well within the standard curve. So there was only about 4.5% of the starch remaining. So it degraded 95.5% of the starch in the solution. Pretty good. My spit, pure spit, and spit that was diluted 1 to 10 were at 0%. So there was no starch remaining. And then my spit at 1 to 100 dilution was around here. There was around 11 to 12% left, but it fell outside the standard curve. So I'm guessing at that point. I will repeat this assay and try to have my spit fall within the standard curve. But for right now, just know that a 1 to 10 dilution of my spit degraded 100% of the starch in the solution. Which leads me to the question, how much starch can my spit metabolize? 5 microliters, or 0.005 milliliters, of my 1/10 diluted spit metabolized 1 milligram, or 0.001 grams, of starch in 30 minutes at 37 degrees C. So what I want you to do is take a moment, do some math, and tell me how many grams of starch can 1 milliliter of my pure spit convert to glucose in 1 hour at 37 degrees Celsius. So take a minute, pause the video, do some math, and then come back. All right, so you should have got to the solution of 4 grams of starch were converted to glucose per milliliter of spit per hour at 37 degrees C. This sounds like quite a bit of starch from my spit. So if I have around 5 milliliters of spit in our mouths at any one time, and this was a Google search, so the range for a normal person is 1 to 10 milliliters, and I'm feeling pretty average today, so I'll say I had 5 milliliters of spit in my mouth today. Theoretically, I can convert 20 grams of starch to glucose in an hour, which still sounds really good. But when I actually do the math and actually look at how much starch are in saltine crackers, I find that my saliva can convert 2 saltine crackers worth of starch to glucose, which was a little underwhelming, and I was fairly disappointed. So it doesn't look like I'm going to be able to sell my saliva to refineries to make ethanol anytime soon. Sorry, to convert the starch to glucose so the yeast can eat the glucose to make ethanol. So I'm not going to make any money off of my spit today, which is a bit of a sad way to end my day. So for tomorrow, I want you to think about a question. I took saliva from myself yesterday and I did the amylase measurements. If I were to do the same thing for Pete, do we expect to find the same, more or less amylase activity in Pete's spit? And why do we think that? I mean, obviously, I will probably lose an arm or two getting the saliva, but we're going to try. So come tomorrow ready to have a discussion around this and come with an argument or two for why you believe what you believe. So I want to thank everybody, especially Pete and his boxes. So have a good one.